Jeff LaFrenierre, and he is from the Glacier Environmental Change Group at the Bird Polar Research Center. His entire group pretty much got on a plane last night and flew to Peru, so they have left him all by himself, but he's joining them in about a week because their research continues down there. In fact, they have a blog. Maybe at the end we'll have you give this the address for, but if you want to follow along, there's a blog where they're posting all the results of what the work they're doing. So, okay.
All right.
All yours.
Great. Hi, everyone. Thanks for letting me have a little bit of your time today. I do a lot of lecturing in front of college classes, but the lecture that scared me the most was the one I gave for my sister's kindergarten class. She's a kindergarten teacher in Colorado. And that was an intimidating audience. Those kids, they didn't let anything slide, that's for sure. So I'm expecting somewhere closer to that end of the spectrum with you guys rather than my normal audience. So I've been asked to talk to you today a little bit about sort of wrapping up thinking about the impacts of climate change. My understanding is the last couple of weeks we spent a lot of time thinking about the science of climate change. I want to share with you a little bit of the work I do that examines how the changes that are happening in the environment are impacting the lives of people. So as Jason mentioned, our group, the Glacier Environmental Change Research Group, really looks at the intersection of the social science and the physical science, thinking about climate change, particularly in glaciarized watersheds. Most of our group does work in Peru, and that's why they're all going down there. I actually do my work in Ecuador, and so we're going to be talking a little bit today about the research I'm doing in my dissertation in Ecuador and thinking about the case study that I'm working on there. So I'm a PhD candidate. That means I've done everything I need to do to have that doctor except for finish the dissertation, just that little tiny thing holding me up. I expect to be done in January or February next year, and hopefully we'll be on as a big person when I'm all done with this. I study what I study because I come from a background really in development. I've spent a lot of time volunteering with a group called Engineers Without Borders. I don't know if any of you are familiar with that group, but it's a group that is either has professional chapters or student chapters, and you do things like build water systems or schools or latrine systems, things like that. And our group was building water systems in Southeast Asia, and then we started doing some projects in Ecuador below this big, beautiful mountain called Volcan Chimborazo, which is about 21,000 feet tall. It's the tallest peak in Ecuador. And the communities there are drawing new water systems, including one that we built, from springs that are at the base of this mountain that is covered with glaciers. This mountain is just south of the equator, but it is tall enough that it is ice covered. So we'll talk a little bit about how that happens in a minute. But my research really came about by people asking the question in the community, okay, well, this is great that you've built a water system and these springs seem to be doing okay. They're better than the ones we've had. But we see that the ice and snow on the mountain is changing quite a bit. So what does that mean for our water supply 20 years from now? So that's how I got to be standing in front of you today, is that question being asked and me going on with that body of research. So what I want to do today is I want to spend a little bit of time kind of giving you a background of glaciers in the water supply system, the hydrology of glaciers, if you will. So I don't know what your experience with hydrology and glaciology is. I'm certain you've gotten some of those things, but if you have questions or things that don't make sense, please just jump in at any time and I'll try to work you through that. And then what I want to do is move on and talk about my real world situation that we're looking at. This is a real world climate change problem that people are having to address. It's not something that they think about abstractly like we can. Oh, it might be hotter next summer, or we'll have to turn the air conditioner up a little bit more. These are people who are seeing their livelihoods change because of changing conditions on the ground right now. So that's the case we're going to talk about. So before we get started, I want you to think about this graph. And I'm going to ask Jason to pass these out so you have a copy closer. And we're going to come back to what this graph is telling us. But this is the root of the problem, what we're looking at here. You're looking at a time series data, a set of data that start in mid-June of 2011 and run through the end of January of this year. And it's from a gauge that's placed on a canal near Chimborazo a little stream gauge. There's a kind of a glide picture. Is there any way to dim the front lights at all? That might make it a little bit easier. There we go, yeah. That's measuring the flow in this canal. So what is the problem that this graph is describing? Anyone want to take a crack at it? Well, there's irregularity of flow, definitely.
It seems as if you read it from July of 12 to January of 13, that the lower points are getting lower.
They are getting lower, that's true. Part of that is because we're going through a dry season. I'll talk about the climate there, but this is a drier time of year that we're looking at.
And the higher points are getting
The higher points are getting higher, that's true. What else?
There's a longer period of time for those low points, like it's staying lower for, yeah, the duration.
Okay, what do the low points mean? Why do we care about those low points or those high points?
Water demand.
Exactly. So this is a graph of demand in the canal. This canal is extremely highly regulated. Every liter of water is partitioned out for every hour of the week. We'll talk about why a little bit later on as well. But the bottom line is that for every given hour of the week, this yellow line represents demand is being fully met by the water that flows into this canal. And as you can see, over the course of 6 months, that doesn't happen most of the time. So that's the problem that we're trying to deal with. We're going to try to come back to this later on and figure out what we need to learn in order to try to answer the question of why and what this means for the people who live there, okay? So just keep that in the back of your mind. So now we'll go through a little bit of background. Has anyone actually been on a glacier before? Couple people, yeah? Which one have you been on?
In Glacier Park and
The Grinnell Glacier, the one you can hike up to, yeah? Anybody else? Pastoruri in Peru. Oh, very good. That's where most of our group is working in the Cordillera Blanca. Yep. So as you can see, glaciers are rivers of ice. This is a time series from the Mendenhall Glacier in Alaska, and it's showing how Glacier Retreat has occurred over a period of about 4 years. Did anyone go see the Chasing Ice documentary when it was here, or the film? Yeah, hopefully it will be. It's really, really cool. So this guy named James Baylog has done a project where he's set up cameras at about, I think, 60 different glaciers around the world. And they automatically take pictures every day, I think, or maybe a couple times a day. And he's built this amazing time series of images showing how glaciers are changing rapidly over relatively short periods of time. And this film talks about the experience of putting in these cameras and the a little bit of the climate science behind it. It's a little bit of a, sort of a hero film. This is really cool. A lot of really cool imagery of glaciers, a little bit of climate science. The background here, though, is that you're seeing a glacier that's shrinking, even though it's moving forward. So, have you talked about why glaciers formed? Does everyone have an understanding of that from this week? How glaciers snow accumulates and it packs down and it compresses and it gets really, really dense. If you put it on a slope, it's going to start oozing like a plastic material. So a glacier, by definition, is a body of ice that is flowing, right? So that's what we saw here. Let's run it again while I keep on yapping so you have something to look at. I think it's going to flow again, yeah. So you see the glacier is flowing down the hill. You have accumulation of snow at the top end and you have melting of the ice at the bottom end. And the balance between those two determines whether or not a glacier is growing or is retreating. As you can see here, what's happening is even though that glacier is flowing, it's melting more rapidly at the bottom than it's accumulating mass or accumulating snow, which is converting to ice up at the top, right? So that's why this glacier is retreating. Now think about, those of you who have not been on a glacier, have you ever been in a place where glaciers have been? This is a trick question, right? Because we live in Ohio, exactly. So roughly 25,000 years ago, there was an ice sheet right here in Columbus. Anyone want to take a guess at how thick that was? What is that? Ah, okay.
Mile and a half, 2 miles.
That's very thick, not quite that thick. It is impressively thick, but it's about a half-mile thick. But what that means is you think about, say, what's the tallest building in Columbus, downtown? I'm not sure which one it is. Which one? Rhodes Office Tower. So think about that times 3 or 4 height, and that's how thick the ice sheet was here. Anyone want to guess at how much colder the temperature was on average, on a day-to-day temperature average, when the ice sheet was that thick here? Just different from today. How many degrees colder on an average day was it 22,000 years ago? 70, 100? Try 12 to 15 degrees Fahrenheit. Really. That's all it takes to get an ice age to happen. So glaciers are extremely sensitive to small variations in temperature change. All you need is a little bit of ice that starts to build where it doesn't melt, and it keeps growing and growing and growing, and pretty soon, you put enough years together, the ice sheet's going to get really big and start moving, and that's exactly what happened here. And it will probably, regardless of our efforts to counter this, at some point in the future we can expect there'll be further ice ages, and this area will again be covered in glaciers, one way or the other. So one of the things that we know about glaciers then is that they are very, as I just said, very sensitive indicators of climate change. And so you might think of them as a canary in the coal mine. Is anyone familiar with that phrase, besides it being a pretty cool police song from way back in the day? The canary in the coal mine was what the miners brought in to test essentially if there was poisonous gas. And if the canary dropped off your shoulder or dropped dead in the basket, that meant that you probably needed to get out of there in a hurry, right? So glaciers are working very well for us as we think about climate change and what is going on in our atmosphere. And so for people who don't believe that climate change is happening, I ask you simply to look at the glaciers in all different parts of the world and see how they're behaving. And what does that maybe tell us about what's happening in our atmosphere? So this is the Athabasca Glacier in Alberta. This is on the Icefields Parkway. If you've never been to Jasper or Banff National Parks, in there you have everyone else, you need to make that on your bucket list of places to go. It is extremely cool. You can walk on this glacier. It doesn't look like that anymore. It looks like that as of 2005, and it's shrinking even more rapidly in recent years. If we go down to South America in Peru, Coricalis Glacier off the Calcaya ice cap, which is where Lonnie Thompson has done a lot of his research. You probably have talked about that. This is a picture from him in 1978, I believe, and that is 2004. You can see that not only has the glacier shrunk back, there's a gigantic new lake that's formed there. And in the Himalaya, in Tibet, this is a glacier just north of the Everest region, and that's what it looked like just a few years ago. You can see these gigantic lakes are forming. There's a whole other topic we could discuss about the hazards associated with Glacier Retreat. I've been to a glacier immediately south of Everest in Nepal called Imja. This glacier started retreating, as all glaciers in the region have been retreating over the last century. And in the early 60s, some meltwater ponds started to form on the tongue of the glacier. The lake that is now there is over 2 miles long, and it's estimated to be 300 feet deep at its deepest place. So this is a massive amount of water that's built up, and it's set up behind a dam of loose rock and melting ice. What do you think is going to happen to that lake at some point in the future? All the people who live downstream of this lake are extremely worried about what this means for their livelihoods, their communities, their safety. It turns out that this lake is in the drainage that you walk up if you are going to walk to Everest Base Camp. So you have thousands and thousands of people who are in this drainage all the time, living, tourists, that sort of thing. And this is a real hazard that people there just don't quite know yet how to deal with, partly because it's so remote. There are no roads to it. How do you deal with a lake that big that is growing that rapidly? All right. So I'm getting off on a tangent. I don't need to do that because I'm going to run out of time. But there are lots of issues that we need to think about in terms of Glacier Retreat and the intersection of human society. The bottom line is, though, that of all the glaciers that are being monitored worldwide, most of them are retreating. This is a figure from the World Glacier Monitoring Service that shows basically the number of glaciers that have been monitored on an annual basis, as well as whether or not those glaciers are growing or retreating, okay? So red is retreating, blue is growing. And you can see that retreating glaciers far outweigh the number of growing glaciers, and in the last 30 to 40 years, the ratio has approached about 30 to 1. So most of the glaciers in the world are retreating, right? 30 are retreating for every one that's growing. Anyone want to guess at why certain glaciers may be growing even as we know our atmosphere is getting warmer? What are the two things that cause glaciers to form? Precipitation, right? So you need an input of snow or rain. Rain would not be good. So what else do you need to control? Temperature, right? So what do we know about temperature and its relationship to the ability of the atmosphere to hold water? Is this anything any of you guys have ever talked about in the past or have any experience with? The warmer it is, the more moisture is held in the atmosphere, exactly. So in areas where the temperature has increased, but it is still a little bit or not a little bit, well below the temperature that is necessary to form glaciers, but you can get more moisture in the atmosphere, you can see greater amounts of snowfall. So there are a few places in the world where glaciers are actually growing even as the atmosphere warms, because it's still plenty cold enough, but there's more snowfall that's falling. And one of those areas is actually in eastern Antarctica, which is why sometimes you'll hear climate deniers say, oh, the glaciers in eastern Antarctica are growing, so that's obvious evidence that global warming is a hoax. Regarding all the other glaciers, those don't matter. But yeah, of course they're growing because there is more moisture in the atmosphere there because it's getting a little bit warmer. We also see this in parts of the Himalaya and the Karakoram range in Pakistan, where changing patterns of precipitation are bringing more snow in the wintertime and less monsoonal moisture in the summertime. So more snow is accumulating even though the temperature and precipitation patterns are changing and those glaciers are growing. But the bottom line is, what you need to remember for right now is, if you're a glacier on this planet, for the most part, you're shrinking. And in many cases, you're going away rapidly. The snows of Kilimanjaro, if you're familiar with that, right? Those glaciers will probably be gone in about 10 or 15 years. And the only place on this planet you'll be able to find Kilimanjaro glacier ice is going to be in the freezer of the Bird Polar Research Center. Yeah, you had a question.
I was just wondering about your comment about where they are growing. Is that still a temporary effect though? I mean, is that something that as our global temperatures do increase, will that overall temperature offset the abundance of precipitation that's causing them to grow? Like, is that a short-term effect?
In many ways, the answer to that question is site-specific, because there are so many things that go into any particular glacier. How much snow falls on it, how much snow avalanches on it from the surrounding peaks, how much sun gets on it, or how much shading there is, right? So there are lots of things that are going to control. The bottom line is that there are still many areas where it's very cold and below freezing the predominant part of the year. But that balance is it's right there on a tipping point usually for a glacier, that it doesn't take much change even for parts of the year to see some pretty dramatic changes, right? So Greenland is a good example, and I'm not a glaciologist certainly with Greenland's ice sheets, so I'm talking a little bit outside my expertise here. But last year was one of the first times on record that there was evidence of melting pretty much across the entire Greenland ice sheet, not just at the fringes. And this in the glaciological community was seen as being a really big deal, because this is indicating a level of warming that there's no human evidence of in the past, all right? The bottom line is, in Greenland, it's still below freezing on the top of that ice sheet the vast majority of the time. But the fact that it is getting warmer and there are days in which melting is occurring is going to change that very careful balance of accumulation and melt that allows glaciers to maintain their size, shrink or grow. So to sort of answer your question, it's hard to say, because in any given glacier there are lots of different things that can happen. There are still many places where it's going to stay very cold, but anything that changes both the temperature and the precipitation is going to have an effect one way or the other.
Just
Okay.
another reason to show that just ignoring all the other evidence and just looking at that snapshot is not very telling.
That's very true, absolutely. So glaciers are a canary in the coal mine, but any given glacier is not a good indicator, right? Just like any given storm is not an indicator of some sort of climate pattern. It's the building accumulation of evidence. All of these glaciers are changing. That tells us something a lot more than one glacier in Montana changing, right? Thinking about ice mass loss, this is a graph that shows cumulatively how much ice certain monitored glaciers, about 30 glaciers around the world, have lost through time, starting from 1945. And what this graph basically is showing is that ice retreat is accelerating in recent years, and that for every square meter of glacial ice aggregated for these different glaciers around the world, each square meter has dropped about 20 meters in height. That's how much ice is being melted from these mountain glaciers. Does that make sense, this graph? The bottom line is these glaciers are losing a lot of ice. So, what does that mean for us when we are thinking about water supply? So that's where I want to bring this conversation to, and I'm going to run this little graph. Is everyone familiar with the hydrologic cycle and water and where it comes from, where it's going, right? So you have evaporation from the oceans and advection of moisture from the oceans over the land surface in the form of clouds. Precipitation's falling, and some of that water is infiltrating down into the groundwater. Some of it's running off as streams and rivers, being stored as lakes. Some of it's accumulating as snow and glaciers and being stored for long-term use. Some of that water is being evaporated out of lakes and back into the atmosphere. Some of it runs all the way back down to the sea. So we have this whole cycle. The mass of water doesn't change very much. It changes its form. So during the Ice Age, when a lot of that ice or the water was locked up as glacial ice, we know their sea levels were lower, right? They're about 400 feet lower, which allowed the Bering Land Bridge to form and people to walk across from Asia to the Americas.
400 feet?
400 feet, yeah. So during the Ice Age, the 300 to 400 feet, I don't know the exact number. Do you know off the top of your head?
It's a little over 300.
A little over 300? Okay.
Still a lot.
Still a lot, yeah. But so the Bering Strait is not very deep. So all we need to do is lose 300 feet of water and we can walk back across to Asia again. Anyone know how much sea level rise would happen if we lost all of the ice that currently exists in the world, including Antarctica and Greenland?
That'd be scary.
Be about 65 meters, right? Is it meters or feet?
It's meters.
It is meters, 65 meters. So about 200 feet of water growth worldwide in the oceans if we lost all the ice. Don't worry, that's not going to happen. Probably not at least next century or so. But yeah, you know, think about where you're buying land, right? Don't invest in Bangladesh at the mouth of the Brahmaputra River. It's going to get a little dicey there. But thinking about this thing, think about this sort of as an analogy like your bank account, okay? So water and glaciers, and that's what I want you to get out of this message. So this is all of the potential labor that you might have in your body. Think of evaporation as the actual work you're doing to earn money, okay? So this is all the potential money you could earn. Evaporation is the work you're doing to earn that money. Clouds and advection, the moving of that moisture, is the work you've done, but the money you haven't yet been paid, right? Payday comes at the end of the week or the end of the month, so you've got that money there, it hasn't arrived. Precipitation is your actual paycheck, right? So there's the money. Now what's going to happen? First of all, a lot of that money is going to flow right out of your pocket as you pay your rent and you pay your car bill and you do all that. Some of that money, if you're lucky, you can put into some long-term investments. Maybe you own a house, you've got some stocks or bonds. That's what infiltration into the groundwater table would be, water that you're putting in for future investment. So what would a glacier be in this analogy? Savings account, yeah, exactly. So glaciers are your savings account. So that's the money you draw on when your checking account gets a little bit too low to cover that last latte you purchased on your way to school. This is a hydrograph. So a hydrograph is a graph that's showing how much water is flowing or how much precipitation is falling during the course of a year. So this is looking at Peru. Specifically, and the hydrologic year here is actually from July to June, so that's why it's not January to December like we would be used to. And what you see here is precipitation as a percentage of the annual total is very low in July and June. This is the dry season. It's very high in February and March. That's the wet season. So it's a very distinctive wet, dry year. All right? So if this is precipitation, what would you expect stream flow to look like, graphed the same way on the same chart? It would be similar, right? You would expect there to be very little water in streams and rivers when there's very little precipitation. You would expect those streams and rivers to be very full during the time of the year when rainfall is most abundant. And that's exactly what you would see. So these are actual raw data from the Cordillera Blanca in Peru, from several drainages there. So we are seeing that pattern of stream flow matching precipitation. Now, what would you expect to happen if there are glaciers in the watershed, as there are in some of these watersheds? The glaciers are melting, so there's a little bit excess water, but let's pretend for the moment that they are just behaving the way they normally would. So they're accumulating mass during part of the year, and they're providing water during other parts of the year, like we would expect here in the summer. The peak wouldn't be as high, which means, well, the peak isn't high, so what else has to happen to balance this? The low points aren't as low, right? Exactly. So that's what a hydrograph in a glaciarized watershed in this climate looks like. You can see that excess precipitation, excess snowfall is being stored as ice. It's not running off in these watersheds because it is accumulating as ice through time, through years. And it's being released in the dry, hot part of the year when there otherwise isn't precipitation. So if you're a water user downstream, this is a pretty good deal for you, right? This is your savings account for water supply, ensuring that you have enough water year-round to use for primarily for agricultural irrigation. You don't really want to drink glacier water. It's pretty dirty. We'll see some pictures of that in a minute. But it's great for irrigation. And if you don't have that water here, you have a problem here if you're expecting it, or if you don't otherwise have means of getting water to your crops. All right? So those are your savings account. Those blobs represent the money that you have available to you, or in this case, the water you have available to you when you otherwise don't have anything in your pocket. So why does this matter? Well, worldwide, there are probably about 120 or so million people who live in watersheds that get at least half of their water from glacier melt for at least one full month of the year. Think about that. 120 million people rely at least a month of the year on glaciers to provide at least half of the available water. All right, that's pretty significant. That 1 month of the year is typically going to be a dry year in which there is otherwise a dry part of the year in which there isn't precipitation. So that's their savings account. Doesn't sound like a whole big number when you think about 7 billion people, but that is just the half of the water. So if you start adding in, okay, a quarter of the water for a month of the year, then that number gets much, much bigger. Okay, but it's most severe for about 120 million people. Based on this graph, you can imagine where the biggest problem is. It's in Asia, and the watershed of most concern is the Indus watershed. This watershed starts in China, it flows through India and into Pakistan. It provides most of Pakistan's irrigation water supply. Anyone want to guess why this area is of particular concern above and beyond its climate and physical geography? 3 nuclear-armed powers who don't particularly care for each other, Pakistan and India most famously, who are actually fighting a battle, a slow simmering war on a glacier called the Siachen Glacier. You can search that up on YouTube and look for India-Pakistan Glacier War. You can see they lob artillery at each other at 20,000 feet. It's amazing. They're not specifically fighting over water, but they're fighting over territory that holds water resources, right? So ultimately, in a lot of ways, it is about control of resources and control of water. So thinking about what Glacier Retreat means to water supply is a geopolitical problem that we need to think about worldwide. This is a major, major issue that is only going to get bigger in the decades ahead, all right? Questions about any of this? So this is sort of the end of the overview of why we care, what glaciers do, how they play into water supply, and why this is a big deal. Okay. So let's take it back down to Chimborazo, Ecuador. And this is the area where I'm doing my dissertation research. These are actual quotes from people that I've talked to over the course of the last couple of years. As you can see, there is pretty significant concern socially, first of all, worldwide, but here as well, particularly, that climatic conditions are changing, and this is having some serious impacts on their access to water. People in Ecuador are largely, the people in this part of Ecuador, let me clarify that, are largely farmers who rely on rainfall and irrigation water to grow crops for their livelihood. As you can imagine, they are extremely sensitive and tuned in to what's happening in their local environment. And this is a big enough deal that it's become part of the conscious of the country. And I have been in taxi cabs coming out of the airport in Quito, which is a city of 6 million people. It's the capital of Ecuador, where as soon as I explain why I'm in the country, taxi drivers will ask me, why are the glaciers all retreating on our mountain? They're very, very, very sensitive to this, all right? So as we go through this in Ecuador, I want you to really keep in mind this idea that this is not abstract, okay? This is very much day-to-day lives for many, many people. So let's talk about this area, the Los Abras Canal, which is going to be our case study, and this part of Ecuador. So Chimborazo is a big volcano. It's a beautiful mountain. It's a little bit taller than Denali in Alaska. It's actually the point, because it's on the equator, even though it's only about 20,700 or so. It's the point on the Earth's surface in which you are farther away from the core of the Earth because of the equatorial bulge, if you're familiar with the shape of the Earth. All right, so that's good trivia for you to know. If you want to be the lightest you can be on the Earth's surface based on your distance from the core of gravity, you want to do your weigh-in on the summit of Chimborazo. All right? There are about 200,000 people who live in Chimborazo's glaciarized watershed. So you can see it does have a nice little ice cap, glaciers flowing off all sides. Riobamba is the provincial capital of the province of Chimborazo. Many of those people live here in the city. There are about 15,000 people who live in this area called the San Andres Parroquia, and that's essentially sort of like a township we would have in Ohio. Nearly all of these people are farmers, or at least live in households that have had farming as a primary part of their livelihood activity in recent years. Irrigation is very, very important to this area because they have two distinct dry seasons during the course of the year. So this is the tropics. We're 1 degree south of the equator. The temperature variation is, what would you think, very great during the course of the year or not so great? Not so great, yeah. So I lived there for most of last year, and the one thing I could never get used to is the fact that the sun rose at 6 a.m. sharp, it set at 6 p.m. sharp. That never changed. There was never long dusk because the sun goes straight down. And it's a very different experience than we're used to living here in North America with our different seasons. What that means is the amount of solar energy that's getting into the atmosphere there doesn't change during the course of the year. So the temperature is the same over the course of the year. The coldest month, June to July, is only about 2 degrees Celsius cooler than the warmest month of March. What does change, though, is the amount of precipitation. So you have a period like in Peru during March, April, May, in which it's really, really wet. And then you have this period of June, July, August in which it's really, really dry. And then you have a smaller wet and a smaller dry season kind of in between those months as well. But the bottom line is that that dry season is a problem if you need to have abundant precipitation for your crops. Turns out here that if you're a farmer, you need to have 2 crops a year, 2 harvests a year from your land in order to earn enough money to have a sustainable livelihood without doing something else. The rains have in the past generally provided enough to provide those 2 crops, but it's always dicey during the dry season. The dry season, as you saw from those quotes, appears to be getting drier and the precipitation is becoming more variable. At this point in time, essentially, if you do not have irrigation, you have a very, very difficult time earning enough income from a second crop in order to maintain your livelihood on your land. We're going to talk about that in a little bit more detail in a second. The climate, as you can see, there's a lot of climate variation in this area. That's typical of mountain areas where if you change your aspect, the way you face, or you change your altitude, then you would expect to see different conditions. And one of the very cool adaptive strategies that people have had here for hundreds and hundreds of years, thousands of years, is that instead of having one big chunk of land where they have all of their crops growing and that's where all of their activity is, people buy small parcels in different locations, different aspects, so facing different directions and different elevations. That way, if you have, for example, a frost in May that kills off your potato crop at 4,000 meters, you probably still have not had anything happen to your carrot crop or your onion crop that's at 3,700 meters on a south-facing slope, or in this case, because we're south of the equator, a north-facing slope where it's a little sunnier. And so you have a little bit of insurance, and that's the way you diversify your portfolio, is by having little pieces of land over larger areas. Okay. Specifically, the Las Abras Canal is the largest and most important irrigation canal in this area. This serves 1,500 specific households, which total about 7,000 individuals that live within those households that rely on this water specifically for their livelihood activities. All right, so a lot of people who are using this canal. It's the canal that is most heavily fed by glacier meltwater. So of all the glacier meltwater coming off this mountain, this is the canal that's collecting most of it. Okay, so that's a little of the background of this particular canal. So we go back to this graph. Think about this. It's been in the back of your mind, I hope. We talked about what our problem is. We talked about why this is a problem, right? So down here, 60% of the required allocation of water on this particular day was not met, or only 60% was met. So 40% of the people, either everyone didn't get some of their water or a certain percentage of the people didn't get any water. The way this works is you irrigate on an 8-day schedule. So you get a certain amount of water based on the amount of land you own. And so you might get water for 20 minutes or an hour and 20 minutes, depending on the size of your parcels. And you get that for a certain number of hours every 8 days. Small pieces of land get 1 hour, maybe 20 minutes every 8 days. If you don't get water during your turn, you have no recourse. You have to wait until your turn again 8 days later, and if there's water there, then you can get your water, and if not, you wait again 8 more days. You can imagine people who live down canal have a harder and harder time of this, right? Because people on the upper end have better access to the water. Now, there is some control, and this is all tightly regulated, so you can't theoretically take water out of the canal when it's not your turn, but that doesn't mean it doesn't happen.
Are they storing the water when there's an abundance?
That's a great question. They do not. They don't have any sort of reservoir capacity. And so when we talk a little bit later on about how we resolve this, that's the obvious thing, isn't it?
Yeah.
Is that you've got excess water here that's flowing more than people need. How do you get this water down to here, right? Now that's going to cause, that's going to take some investment. It's pretty expensive, actually, to build reservoirs. And
Nighttime? When it's
nope.
no?
Anyone want to guess? Anyone else? Rainfall events, yeah. Or in a few cases, when it's really hot and sunny, which doesn't happen here too often at those elevations, you get really high glacier melt. And so you get, even though it's not raining, you'll get a big pulse of water entering the canal from the glacier itself. And so that's where you'll get some of this water starting to peak up a little bit. But mostly this is rainfall.
Is this all regulated by the government? Is this, like, when you say it's regulated, like, and there's control as to how, who gets the...
That's a good question. The government of Ecuador owns all the water, and they allocate concessions to various user groups. So theoretically, the government can come in and say, you can get water this day, this day, this day. That's not really the way it works. User associations themselves manage the water. So you have an association for the Los Abras Canal, and I've had an opportunity to attend a few of the meetings of this group, and they're boisterous, and there's lots of conflict going on over the water, as you could imagine. And to get 300, 400 of the users in a courtyard on a Sunday morning to argue about why certain people are getting more water than others is a sight to behold, let me tell you. But so the government kind of takes hands off. And one of the problems that's been going on here is the government has actually been allocating more water than is available because they haven't until now had a real inventory of water supply in this watershed. Imagine not knowing how much money is in your bank account when you start writing checks. That's essentially what's happening here. And the government has been writing checks in the sense of handing out water concessions to people or to users without knowing if there's enough water there to meet those demands. This canal is actually based on a law that said that the river coming down off the mountain is called the Rio Mocha. And at the point where this canal is diverted, this canal association is guaranteed 60% of the water that is flowing in the river at that point. That supposedly means roughly 900 liters per second, 909 liters per second. They haven't been able to get 909 liters per second, 60% of the flow, since probably the mid-'80s. Right now they're averaging about 450 liters per second. In fact, this line right here, full allocation, represents 437 liters per second. For the most part, a few times it's a little bit higher or lower depending on how the water's allocated, all right? So they supposedly they're supposed to get 900 liters. They're only allocating half of that. They've already adapted by cutting off their allocations by 50%. And they're still not reaching that threshold at this point in time. So this is an even more severe problem than it looks because over the last 20 to 30 years, they've already cut as much water allocation as they possibly can. Any other questions about this?
When you have parcels scattered all over, how is it that you are able to get that irrigation water to those very, I could see all kinds of opportunities for shenanigans with that, because how do you know if the water that you allocated to someone gets to them and not to their neighbor?
Well, you are the one who's out there on the ground controlling the water getting to your field. Now, when you have parcels scattered all over the place, some of your parcels will be irrigated, some of them will not be. You will want to irrigate those parcels that are the driest or that are growing a crop that is most sensitive to water shortages. Other crops where you have a little bit more flexibility, maybe grass for livestock, you can rely a little bit more on rains than you could if you were growing beans or corn, for example, all right? So that's kind of the first part of the question. You don't necessarily irrigate all of your parcels, but you have to have crops growing on some of your parcels at least to get that second crop, right? And if you don't have any irrigation supply at all, then you're becoming more and more stressed. We're going to talk about that in more detail in a few minutes. What else? What might be causing this problem? So we see there's a problem. There's no question that we have an issue here. So based on what we've talked about, as well as other things you can think of, what might be causing this?
You mentioned that the rainy seasons were not as rainy and the drier seasons were drier. So wouldn't that impact?
Absolutely. So a primary cause could be changing precipitation patterns in particular, as well as changing amounts of temperature which impact evaporation and water demand from the vegetation and that sort of thing, evaporation from the streams. So basic climate change is one potential cause. What else?
As the water comes down the canal, obviously people are drawing out. So if you're at the bottom of the canal, you're sort of out of luck.
That's very true. So there's a lot of stress between downstream and upstream users in this canal. One of the things that we have to think about then is infrastructure. How might a canal lose its water without anyone actually taking water out of the canal? It's structurally unsound. Or what if it's just an unlined dirt ditch, which is what the majority of this canal is? That water is just going to infiltrate into the ground, right? We're going to see a picture in a few minutes that shows the canal flowing through a very barren area except for this wonderful green grass that's growing right along the banks of the canal. What is watering that grass? The canal, exactly. All right, so we have infrastructure issues.
You had mentioned that in the mid-80s,
Well, that's another possible hypothesis, is that glacier melt is changing, right? So one of the things we didn't really discuss, but it's kind of important to consider, when glaciers are melting, you would expect more water to generate, right? But eventually, the size of the reservoir you have available to generate meltwater is going to shrink. So you end up with a bit of a curve. There's nothing I can really draw on. So as glaciers start to melt, you would expect more meltwater to be generated, right? But eventually, the amount of ice that you get available to generate meltwater will pass a critical threshold. At that point, you get less and less water generating, even as the glaciers are melting faster because the glaciers are getting smaller. All right, so it's a question of mass. So it's another hypothesis. Glaciers on Chimborazo have changed enough to where there isn't enough water that's being generated by those glaciers to support the river that's feeding this canal. Okay, so one other thing that could be happening here. Think about it from a social side. Population increase. How about just more broadly, water demands are changing, right? So remember, I just said that the government hasn't actually gone out and done a water resources inventory, yet they're still handing out concessions for water supply. So we're going to see a picture of some of the pipelines here. There's a bunch of new pipelines on this mountain that are drawing water from springs that are upstream of this canal input. That means that's water that would naturally be running off that isn't reaching the canal anymore, all right? So there's 4 different possible causes for what's causing this problem. I meant to bring this in earlier, but I do want to point out that in this area, not just the Las Abras Canal, but in that whole paroquia, 15,000 people, nearly 70% of the people say that at least sometimes they either receive only a part or none at all of their water supply. So this is a very widespread problem.
I don't know. Yeah, I'm thinking this, like, you're talking about water for, like, crops and stuff. What about day-to-day water, like to?
Domestic water.
Yeah.
Yeah.
Where's that in this scheme of things?
Well, that's another problem. So you don't want to drink glacier water. Again, I'll show a picture shortly because it's a lot of sediment, very high mineral content. It's very silty, dirty. So you want to get your water from springs and other sorts of things. So generally speaking, people will develop water systems from springs, many of which are located on the mountain, that aren't glacier melt specifically, but are natural water coming out of the ground, and pipe those and use those for domestic. But there isn't enough spring water to provide irrigation, so you use that glacier melt to irrigate your fields. The problem, though, is, and we're not capturing it with this graph because this is just the Las Abras irrigation canal, those springs are drying up as well. One of the questions is, how is Glacier Retreat, in addition to climate change, impacting spring discharge? So at the same time that people are seeing their irrigation supplies diminish, the springs that they use for their community domestic water supplies are shrinking and becoming less certain, more uncertain. And so that's one of the reasons that's drawing people to build new pipelines higher up the mountain below the glaciers where there are other springs, but that's taking water that would otherwise flow into the irrigation canals. So it's kind of a messy situation, but you get where we're going here?
Is it safe to say that the springs are fed by precipitation?
it's not safe to say that for sure. One of the area of research in my dissertation that I'm not going to be able to get is to specifically tie how much glacier melt influences spring discharge in the mountain. To me, my hypothesis is that a lot of that water that's infiltrating out from underneath the glaciers is feeding those springs. And as these glaciers shrink, that's one of the reasons why springs are getting smaller. I don't have the data to prove that yet. That's a problem for later on.
Do they collect rainwater? You were talking about they don't really collect when there's an overflow in the canal, but do they have cisterns or a system that they can?
Some people will collect rainwater, but most people do not. And one of the reasons they don't is, and this is a whole other level of complexity that we're not even going to get to in this case study, is Ecuador is a very volcanically active country. And it turns out there's a volcano just about 30 kilometers to the east of Chimborazo that's active called Tungurahua. Occasionally you'll see news blips about it. Tungurahua throws out a huge plume of ash. So next time you hear Ecuador, keep in mind it may be this volcano. So the rainwater tends to have a lot of sulfur in it. Yeah. Okay. How am I doing for time? Ooh. Okay. So we got 5 minutes to design a research problem and to think about what we're going to do, what information we need. Okay. So we have a problem. Okay. We have a hypothesis. What are our research questions? There are really 4 research questions that I've come up with. And this is that picture I wanted to show you, the canal, the grass, right? That's water loss from the canal. So what are my 4 research questions? These pictures are my clues, so help me remember what my research questions are. First of all, why is the canal not getting enough water? So if we talked about potential explanations, what is the reason for why this is happening? What does this mean for people? How are they dealing with the fact that they aren't getting enough water? How are they adapting? Are they changing their crop production? Are they maybe investing in other sorts of economic activities? What's going to happen in the future? So those are the 4 questions I'm trying to answer. What information do I need to answer these questions? This is the root of my dissertation. So thinking about how I'm designing my research program, these are the questions I want to answer. What do I need to know? Geology, a little bit as background, but specifically, what do I need to find out? I'm making a possible hypothesis that Glacier Retreat is causing this problem, so what do I need to do? Measure glaciers and try to figure out if glaciers are changing, right? So that's part of it. Okay, we have a hypothesis that says, maybe our precipitation or temperature patterns are changing. So what do I need to do there? Go back and try to reconstruct current climate, compare it to past climate, and see what's going on there. And that is not easy to do in a developing world country where there is not very good data. And that's been a huge problem for me. Okay, so if glaciers are contributing water, what's maybe one of the questions I ought to ask, thinking about all the water flowing into this canal? How much of that water comes from glaciers, right? So glaciers are important, but what if they only contribute 10% of the water and 90% of the water comes from springs? Or what if they contribute 90% of the water and 10% comes from springs? So answering that question is something that's important I need to deal with. How do people use water, right? That's important to know, to understand. We have these broad assumptions, but really kind of getting down to the nitty-gritty of how people are using water is something I need to figure out. And then lastly, the last question I have to ask is, who's going to be vulnerable in the future if conditions continue to change, right? So we're not just trying to describe what's happening now, we're trying to figure out what might happen 10, 20, 30, 50 years from now in this system, because changes are going to continue to occur one way or the other. So very briefly, I don't want to leave you all hanging. I have learned some things, and I want to show you a little bit what I've learned. This is a map of Chimborazo's glacier cover in 1986. I determined this from a satellite image from the Landsat satellite. Wonderful thing that we have, your tax dollars at work. Hooray for the Landsat satellite platform. Be proud of that. That is how much ice was left in 2012. It's lost about 20% of its ice area. The 2 largest glaciers have retreated 3/4 of a kilometer, right? Half mile essentially. So again, 86, 2012, 20%. 20% in 25 years. These dark areas are debris-covered glaciers. I won't bore you with that because we're out of time, but there's a whole other dissertation in there somewhere. Is the climate changing? This is a very tough one to answer, and I'll go through this very quickly. Don't bore yourself with the graphs. This line essentially represents that the mean temperature is increasing at 2 weather stations that are relatively near the mountain. since 1986 during the course of this glacier change. It's increasing about 1/10 of a degree Celsius per decade, which doesn't sound like a whole lot, but remember, it only took us 10 to 15 degrees Celsius to get, I'm sorry, I said it's 10 or 15 degrees Fahrenheit, 6 to 8 degrees Celsius to get us into an ice age, okay? So these small changes, this is pretty consistent with what's been found throughout the Andes. So we have a pretty good idea that, this is maybe reasonably accurate. This is a very ugly graph that's looking at the relationship with El Nino, the El Nino Southern Oscillation, and how that impacts climate. Don't worry about all of that. But basically, this blue line is showing us that there are periods in which it's drier, periods in which it's wetter, but it really doesn't look like it's changing very much, does it? So according to the data that we have, which admittedly is relatively minimal because data collection here has not been very good, but from the information I have, it doesn't look like precipitation's changing at all. So it's getting warmer, but there isn't a whole lot of change in rainfall. But what about those quotes that we saw? What are people's perceptions? So these are results of surveys that I've done in 60 households surrounding the mountain, asking them questions about their environment, very open-ended questions. What is your climate like now compared to what it was when you were a kid? Is generally the way I've asked that. I threw out anybody who didn't live where they lived for at least a decade. So this is just reflecting people who've been here at least a decade. Most of these people have lived there their entire lives. Green means something is increasing, red means something is decreasing. Anybody who answered the question, who mentioned weather variability, said that variability is increasing. All right, what does that mean if you're a farmer? Is weather variability good if you're a farmer? No, it's very bad, right? Because you need to know when the rain's going to come and when it's not going to come. And if you don't know that, especially in an area where your climatic cycle during the course of the year is built on rainy seasons versus dry seasons, you cannot predict that. You have a very difficult time effectively planting your crops and knowing when to harvest them. Temperature changes. Some people say that they're decreasing, some people say they're increasing. Most people don't say anything at all. Now that's weird because we have a temperature record that's showing an increase, right? People aren't perceiving that. What they are perceiving is that precipitation is decreasing. Almost everyone who had anything to say about precipitation, again, open-ended questions, so they're not being asked specifically about precipitation, just how are things changing or how are they now compared to how they used to be, says it's getting drier. But we have a precipitation record that doesn't show that. So what do we do with this? We have people saying one thing and records showing something else. Who do we believe, or what do we believe? Do we throw people's perceptions out the window just because, it's feelings rather than hard data? I would say that I would trust the opinions of people who make their living off the land a lot more than I would 2 rain gauges that have been monitored for 30 years. So given the choice between the two, I'm not going to discount the idea that precipitation patterns are changing because the people who are most in tune to the problem say it is. And they're saying it independently of one another, and they're saying it without prompting. All right, so I think there's very much fire behind that cloud of smoke. Everyone notices that Chimborazo snow and ice is retreating. We know that. We saw that from the graphs. That matches. Everyone says agricultural production is decreasing and becoming worse. So therein lies our livelihood problem. And here's our climate change affecting people day to day. Well, one of the reasons, again, is that this is an area that receives very little temperature fluctuation during the course of the year. So we are more in tune to the fact that, hey, it's 80 degrees in March, because we don't experience that here. Here, the temperature is a little bit warmer, but considering that the temperature doesn't change day to day, I think that would be a harder thing to perceive. You see that manifested in your snow line changing, but you aren't necessarily going to feel that. The precipitation is what you're really going to notice. One of my hypotheses about the precipitation is that the total amount of precipitation falling hasn't changed, but that it's more intense when it does fall, and it happens less frequently. And there's some anecdotal evidence from talking to people that they are experiencing that. So instead of getting ½ inch of rain every 4 days, that's a bad number, but roll with me, they're getting 1 inch of rain every 8 days, right? The bottom line is that people here who used to almost exclusively earn their income from agricultural activities no longer are able largely to do this without having to find some sort of external income. Only 28% of people who I interviewed still earn all of their money from agriculture. 75% of those people are irrigators. So if you're not an irrigator, you're pretty much having to do something else. And what does that mean if you're in Ecuador? There's not a whole lot of jobs in this region, certainly in rural areas. Just like the United States, there aren't jobs in rural areas. So what do people do? They move to the city, at least part of the year. What if your cities don't have jobs? You become impoverished, or you move here, right? There are 250,000 Ecuadorians who live in the greater New York area. Most of those people have come from agricultural areas in the last 20 to 30 years. There is a direct connection between changing agricultural livelihoods in the developing world and immigration to developed countries like the United States. So that brings the problem back down to us. What this also means is that because people are migrating away, at least during the day, if not permanently, the community cohesion is significantly changing here. You very rarely see men between the ages of 20 and 50 in these communities during the daytime, because those are the ones that have had to move away for work, at least during the day. In many areas, houses are now abandoned because there's just no point in trying to earn your income from agriculture anymore. There's not enough water. So there's large areas, especially in the warmer, drier regions down near Riobamba, where you see abandoned houses like this. So this is a significant change in the pattern of life and cultural life in this region. I imagine I am out of time now, so I'm going to pass by this one and say I want us to spend one last moment on this. So I'm thinking about vulnerability in the future, and it turns out that soil quality is also an important variable, as well as irrigation access. There are two different types of soil in this area. One of those soils is good, and it's great, it's organic, it grows your crops very well. One of them is pretty bad, it doesn't have a whole lot of good material. But if you have irrigation water, you've been able to get around past that bad soil because you have enough water to work with it, okay? So thinking about in the future, who are the people who are most likely to be vulnerable to future changes in their climate and their environmental system and having to adjust their livelihoods? What do you think people who have good soil quality and irrigation are likely to are they likely to see a lot of change? Are they vulnerable to particular? No, that makes sense, right? So they're probably in pretty good shape. What about people who have bad soil and no irrigation? You would think so, but it turns out that's not true. Why?
They're doing something else, already getting their money.
They've already done it, exactly. They've passed this stage. They've abandoned their homes and left their communities and immigrated. So future vulnerability isn't real high for these people. So the question is, who is vulnerable to future change? Well, people with good soil and no irrigation access have some concerns, but the ones that are most at risk are probably the people who live in bad soil areas but who do have irrigation, because those irrigation supplies are less and less regular, more and more variable, and they don't know from year to year, season to season, whether or not that water is going to be there. So what do we still need to learn? I didn't answer the question of why, what proportion of water is glacier melt. I'm still working on that. The bottom line is I get to do lots of water sampling and do lots of plots like this, and that's how I'm spending my next 6 months. Come back next year and we'll talk about that. Okay, so we kind of got through it.